Okay, this is still section 3.3, and this is going to be the second video in this series. So go down to where we're talking about the rational zeros theorem. The biggest thing to think about here is that our zeros may be fractions. Remember that rational is just another word for fraction. Mostly what the rational zeros theorem says is that if this P over Q is a zero, then what you find out is that P is going to be a factor of the constant and Q is going to be a factor of the leading coefficient. All right, so the first thing that we want to do then is when we look at example number 3 and using the rational zeros theorem, we've been handed a polynomial. What we want to do is we want to find the factors of the constant and we want to find the factors of the leading coefficient. So when you look at our example here, our constant is the number 4. I have that hidden from you a little bit, but our constant is 4. What are all of the possible factors of 4? Well, you could have a 1 times a 4 and a 2 times a 2. So 1, 2, and 4 are my factors of 4. And what are my factors of my leading coefficient? Well, we've got a 1 times an 8 and a 2 times a 4. So my factors of my leading coefficient then are going to be 1, 2, 4, and 8. Now, I'm going to show you a method of doing this. You cannot write this as a final answer, but part A asks me to list all of the possible rational zeros. So let me just kind of walk you through what my brain is doing. This is not normally something I write on paper. It's just what my brain is doing. So you'll notice that P over Q, P is the factors of the constant. So this is the 1, the 2, and the 4. Over Q, the factors of the leading coefficient, the 1, the 2, the 4, and the 8. So the way that I like to think of this is that these are fractions. So I'm just going to take them all, and I'm going to be very methodical about this. So first I'm going to do 1 divided by 1, 1 divided by 2, 1 divided by 4, 1 divided by 8. That takes care of the 1 on top. And then I'll do the same thing with the 2. So 2 divided by 1, 2 divided by 2, 2 divided by 4, 2 divided by 8. One of the things that you want to realize is that as you go through, if you have a duplicate, if you have something that you are repeating, throw it out. Don't keep it twice. And then the last one that I'll do is 4 divided by 1, 4 divided by 2, 4 divided by 4, and 4 divided by 8. So that's the methodical way that I'm going to go about this. And this is not something usually that I write down. This is just what my brain is doing. So in this particular question, I'm asked to list all of the possible rational zeros. One thing that a lot of students forget on this is that each one of these could be either a positive or a negative. All right, so going back to this idea up here, let's do the 1. So 1 divided by 1, 1 divided by 2, 1 divided by 4, 1 divided by 8. And that's the very first line I'm going to have. There's my plus or minus 1 divided by 1, plus or minus 1 divided by 2, plus or minus 1 divided by 4, plus or minus 1 divided by 8. And then I'm going to do the same thing only with the 2's. So 2 over 1, 2 over 2, 2 over 4, 2 over 8. The thing is with this one is that I have 2 over 1, but 2 over 2 I've already got listed here as 1. 2 over 4 is a half, and 2 over 8 is a fourth. So none of the rest of my 2 overs are going to be written down because they're all duplicates. So then we'll go over here, and in our brains, we're going to do the 4's. So 4 over 1, 4 over 2, 4 over 4, and 4 over 8. And the only one I'm going to find that I'm going to keep here is just the pos or neg 4. All the other ones are going to be duplicates. All right, so that's a list of all the possible rational zeros. These can't all be zeros, but it's a possibles list. All right, now that we have our possibles list, let's move on to part B, which is asking a different question. It says to find all rational zeros. This is not just the possible zeros. This is the actual zeros. Remember, x-intercepts. And then we're also supposed to factor. So the way that you want to go about doing this is once you have your list of possibles, you want to take out your graphing calculator and you want to graph. And what you're looking for is you're trying to match 1, 0 from this list. All right, and so what I've done here is I actually have a picture of the graph. You can pause the video and graph this yourself to see if you're getting the same thing. And as I look at my graph, I see a couple of my possibles that could work. So you'll notice that this right here is an x value of -1. Okay, so it's an x value of -1. So that's actually the first one out of my possibles list that I think might work. It's just a guess because I'm looking at the graph and I think it looks like it goes through. I think it looks like it's an x-intercept. So what I'm going to do then is I'm going to use synthetic substitution and I'm just going to try x equals -1. So if I were you, I would pause the video, use synthetic substitution to plug in x equals -1 and see if this truly is a good 0. Now, we're back, and I find out that, yes, it is a good 0. Now, on the ones that we did before, you remember that we took the depressed polynomial and we factored that because it was quadratic. Unfortunately, this one is not quadratic. My highest power of this polynomial is going to be to the 3rd power, and so it's not as easy to factor a 3rd power. So what happens is when this is not a quadratic, I need to go back to the graph, and I want to see if I can get another 0 to match. So let's go back to the graph. And let's see here, I'm going to zoom in a bit. This one is a 0, but it's not very pretty. This one is also a 0, but not very pretty. And then this one here, which is where my cursor happens to be, it looks like it might work. So maybe we could try an x equals 4. So when we go back to try our x equals 4, here's the big deal. Don't go back to the beginning. Don't go back and use the original polynomial for this. Use the depressed polynomial for this. So as I use synthetic substitution, don't go back to the beginning. Use the depressed polynomial. Otherwise, it's just not going to work out very nicely. All right, so as I plug in x equals 4 into my depressed polynomial, I notice that I get another remainder of 0. And so I'm over here in my list of zeros over on the right, and I now know that x equals 1 was a factor that worked. And I also know that there was another factor that worked, but I don't think that I have that one ready to uncover. Nope. I did say to go back to the graph for another match. So there's my second one that I have found, x equals 4. Now, what you'll notice is that because I used the depressed polynomial, now my newest depressed polynomial is a quadratic, and so I can solve this as normal. So we like to solve by factoring, and so then I can find my zeros by solving. So I have zeros of x equals 1/2 and x equals -1/4. X equals 1/2, x equals -1/4. All right, let's take each one of our zeros. So we were asked to find all the zeros. We've done that now. The next thing we need to do is we need to factor. So we'll come back over here and we'll turn each one of our zeros into factors. So the first two are going to be x plus 1 and x minus 4. And then the second two are going to be x minus 1/2 and x plus 1/4. And so we want to write our factors out in a product fashion. There's 2 ways to do this, just like there was 2 ways in the last video that I gave you. So option number 1 is that I could use my first 2 factors, x plus 1 and x minus 4. And then for my other 2 factors, I can use the factored version that I found over here, and that's perfectly fine. In fact, remember that one of the things that you always want to do is to make sure that your leading coefficient matches. And if I take a 2 times a 4, that's going to be a leading coefficient of 8. If we go back to the original polynomial, my leading coefficient is 8, so that works out just great. If you didn't use factoring though, let's say that maybe you used the quadratic formula, and so you never saw these factors, then maybe what you would do is you would write this out in the second method. And so you would take your 4 factors and you would multiply your 4 factors together, but unfortunately the leading coefficient is 1, and so you're just going to put an 8 out in front of that so that the leading coefficient matches the original polynomial. Either one of those is okay to do. Now, I'd like to, I've got a graphic here. This is not in your notes. This is something that I just happened to add. And I'm curious if you can tell me how many zeros do you find on each graph. Remember that zeros are the same thing as x-intercepts. And so if my polynomial is a first degree, you notice that there's only one x-intercept. My polynomial is a second degree. You'll notice that on this one I have 2 x-intercepts. Here, third degree, I have 3 x-intercepts. Now there are other ways that I could have drawn these where I wouldn't have necessarily had 2 on the second degree and 3 on the third degree. That's okay. So we'll take a look here. How about on the fourth degree? How many x-intercepts do you see? Now, are you starting to see a pattern? First degree has 1, second degree has 2, third degree has 3, fourth degree has 4. What would you expect the fifth degree to have? And so when you look at this, my fifth degree has, well, we've got 1 here. Come on. 1 here. I have 2 over here, and it looks like maybe just 1 here. That's a total of 4, not 5. But think of it like this. Remember I said that I could have something different. What if this guy came down lower? Now how many zeros, how many x-intercepts would you have on this fifth degree polynomial? You would have 5. So I might have up to the number of the degree. I might not have that many, but I could have up to the number of the degree. Same thing with the sixth degree. Right now there's only 2 that's showing, but if I stretched this vertically, and so did something like this, then I could possibly have as many as 6 x-intercepts or 6 zeros in my sixth degree polynomial. All right, so let's take this into consideration then when we cover how many zeros we may have. Now, a couple things here. These last 2 statements are what we were talking about before about our rational zeros. It only gives, the rational zeros theorem does only give possible rationals. It doesn't tell us whether they're actual zeros. We have to plug those in to find out whether or not they're actual zeros. All right, so this fundamental theorem of algebra then is what I was really just talking about. Every function defined by a polynomial of degree 1 or more is first of all going to have at least 1 complex zero. Okay, so every polynomial has at least 1 complex zero. How many zeros am I looking for? Well, we know that if the degree is n, we're going to have at most n zeros. That's why our sixth degree, it didn't have 6 zeros, but if I drew it a little differently, I could have up to 6 zeros. All right, let's look at example number 4 then. Example number 4, part A, says that we should find a polynomial of degree 3. So degree 3 tells me that we're looking for 3 zeros. Degree 3 that has real coefficients and that satisfies the given conditions. And you'll notice that the given conditions are that, first of all, they tell me what my zeros are, and they also tell me a coordinate on my graph. If I were to plug in the x value of -1, I would get out the y value of 6. So then how do I go about finding this polynomial? This is a work backwards question. The last question, I gave you the polynomial, we found the zeros and the factors. Now I'm giving you the zeros, let's go find the polynomial. So the first thing that you want to do is you want to list your zeros. And you see the how-to list over there on the right side of the page. We want to list our zeros. And so I like to list these as x equals. It ends up being much more accurate, and my students don't forget things when I list it with x equals. So I have an x equals -3, an x equals -2, and an x equals 5. And the next thing I'm going to do is, even though it doesn't tell me to do this, I'm going to find my factors. And the reason is I need factors to be able to find my polynomial. So if we take each one of these then and turn them into factors, we'll have the x plus 3, x plus 2, and the x minus 5. These are my three factors. All right, so then what we'll do is we're going to come over to our function and we're going to multiply our factors together. Now you're going to see something that you didn't expect to see, and that's that a value, that leading coefficient. And the reason I put that in there is because of the fact that they gave me a specific coordinate on the graph. So that's going to change my leading coefficient. So you'll see how that figures into play here in just a moment. So number 1, list the zeros. Number 2, find the factors. Number 3, let A be the leading coefficient. All right, number 4, plug in your x and y values and solve for A. So take a look at what I've done here. I left A alone, but for every x that you see, starting with the original, for every x that you see, notice that I plugged in a -1, and then I set it equal to 6 because of this piece of information right here. Every x value became a -1, my y value became a 6. And so then I'm just going to do a little bit of math. Just by adding and subtracting here is all I'm doing. And then I'm going to multiply and divide on both sides by that -12. So I find out then that my a value is -1/2. So now I'm ready to take what we had up here, and now I'm ready to write my polynomial in factored form. Notice that I have that -1/2 out front. That's the only thing that's changed. Sometimes my lab is going to make you multiply these together. To be honest with you, factored form is fine with me. But if the directions specifically say that you need to multiply these out, then you need to go ahead and multiply. I'm not going to take the time to show you my work on multiplying. Hopefully by now you know how to FOIL and distribute. And so this is what you're going to get when you multiply. Now let's go back to the directions and make sure that we did what we were asked to do. We were asked to find a polynomial. We did that. Our degree is 3. So notice that the degree is 3. And all of my coefficients are real numbers. And it satisfies those given conditions. The only thing that I'm going to say here, point out, is that if you leave your polynomial in factored form, sorry about that. If you leave your polynomial in factored form, it's a little harder to see what the degree is because you can't see that the highest power is 3. But if you take an x to the first times an x to the first times an x to the first, you're going to get an x cubed. The degree is still 3. It's just not as obvious as it is right here when you look at the leading term. All right, let's do another one of these. Same concept. In fact, if I were you, I would pause the video and see if you can do this second one on your own without my help. The first thing I'm going to do is list my zeros. Well, I only have 1 0, but notice that it says they're using a new word on you here, with a multiplicity of 3. What this means, and we're going to talk about this more in a later section, but what this means is that you actually have 3 of these same zeros. You've got an x equals 4, an x equals 4, and an x equals 4. And you're like, well, why would you do that? It makes a little more sense when you write it in factored form. In factored form, you understand, I think, to go from x equals 4 to x minus 4 for your factor. The multiplicity just simply says you've got 3 of these exact same factors. And so that's why I'm going to write it as x minus 4 quantity cubed. Oh, so then I'm going to just follow what I did with part A. I'll start out with writing my factored form. I used an A for my leading coefficient. Then I'm going to take the second piece of information here. I'm going to plug 2 in for all of my x's and set it equal to negative 24. And then I'll just do my math, and I'll get that what's inside the parentheses is negative 8. When I do my division, my A value is 3. My leading coefficient is 3. So now I can go ahead and write that in factored form. Notice that I did leave it in factored form. I did not multiply this one out. It's easier to leave it in factored form. If my lab allows you to leave it in factored form, then I would do that because it's just simply easier. All right, that's going to be the end of this video.